Good day, everyone. Today, we'll be discussing Chapter 4, which focuses on the manufacturing process. This chapter highlights key ideas that help us understand how products are made efficiently and how companies make important decisions in their operations. This chapter includes five parts. First, how production processes are organized. Second, break-even analysis. Third, designing a production system. Fourth, assembly line design. And last, summary. Process selection is a strategic decision of choosing which kind of production process to use for producing a product or providing a service. For example, if the shipper produces only a few notebook computers, they might be assembled by hand. But if production volume is high, setting up an assembly line becomes the better option. Types of layout structures. There are six basic structures for organizing production. Based on workflow patterns, let me go through each one. Number one, project layout. In this layout, the product remains in a fixed location, and the equipment or workers are brought to the product. Examples, houses, roads, or movie sets. Since the product is usually large and bulky, different areas are designated for tasks such as staging materials or managing equipment. Number two, a work center. Group similar machines or functions together. For example, drilling machines may be in one area, while stamping machines are in another. The product moves from one center to the next depending on what process it requires. This is also known as a job shop. Number three, manufacturing cell. A manufacturing cell is a dedicated area for producing similar products. The cell is designed to handle a specific set of processes efficiently. For instance, one cell might produce a single product or or a family of related products. This type of layout is often used when demand requires flexibility but also some efficiency. An assembly line organizes work in a step-by-step sequence. Each workstation adds a part until the final product is completed. It's a straight line process, making it efficient for mass production. Common examples include toys, appliances, and automobiles. Continuous process. This is similar to an assembly line but designed for high volume, non-stop production. It runs 24 hours a day and is highly automated. Industries such as petroleum, chemicals, and pharmaceuticals often use this method because it is efficient for large-scale, standardized outputs. And lastly, product process matrix. Finally, there's the product process matrix, which shows the relationship between product volume and process choice. Standardized products with little variation are suited for highly efficient processes, while customized products require more flexible processes. Conclusion. In summary, process selection and layout design are crucial in determining how efficiently a product or service is delivered. Choosing the right structure, whether it's project, work center, manufacturing cell, assembly line, or continuous process, depends largely on the product type, volume, and customer demand. Thank you. I will now explain the product process matrix, which is a framework describing different layout strategies in manufacturing. So on the vertical axis of the chart, the diagram, you can see the degree of product standardization, ranging from low or one-of-a-kind products to highly standardized commodity products. Then on the horizontal axis, you can see product volume, which goes from low volume to high volume. So let's talk about the position of processes. Along the diagonal of the matrix, we can find the five main processes types. Project is located at the low standardization and low volume side. This is where unique one-of-a-kind products are made, such as buildings or movie sets. Work center also handles low volume, less standardized products where similar equipment is grouped together. Manufacturing cell sits in the middle, producing a limited range of similar products more efficiently. Assembly line is closer to the high volume and high standardization of site, making large quantities of standardized products like cars or appliances. Continuous process is at the extreme end, handling very high volume, highly standardized outputs, such as petroleum, chemicals, or drugs. Okay, so the key insight. In general, it is desirable to design processes along the diagonal of the matrix. That means if a company produces unique products at a low volume, it should use a project or work center. But if it produces standardized products at high volume, it should use an assembly line or continuous process. So, in conclusion, to sum up everything, the product process matrix helps managers match the right production process with the type of product and its demand level. This way, businesses can balance efficiency, flexibility, and cost in their operations. Thank you.
So this slide summarizes the concept of break-even analysis. When choosing equipment, companies face trade-offs between cost, setup time, and production speed. For example, general-purpose machines are cheaper and more flexible, but they are slower, while the special-purpose machines are more expensive and require longer setup, but they are faster. So the break-even analysis is used to evaluate these options by showing profits and losses at different demand levels. So this allows managers to select the most economical choice depending on the anticipated demand. This example applies break-even analysis to a real case. The manufacturer has three options. First is to buy the part, second is to use a semi-automatic lathe, and third is to use a machining center. So each option has different fixed and variable costs. So the results show that buying is cheaper at low demand levels. The lathe is best for medium demand, and the machining center is most economical for high demand.
Designing a production system. There are many techniques available to determine the actual layouts of production process. This section gives a quick overview of how the problems are addressed for each of the layout types. Description are given of how layouts are represented and the main criteria used. First is the project layout. Project layout is a type of facility arrangement where the product becomes the hub of all activities. Materials and equipment are arranged around it depending on their frequency of use and the movement difficulty. Example, in a yacht building, rivets are close to the hull since they are used frequently, while heavy engines parts, which are only moved once, can be stored farther away. Cranes, on the other hand, naman, are positioned near to the hull because they are consistently used. Sa madaling salita, ang sa project layout, everything revolves around the product mismo. Task ordering is also very important here. Kasi may specific sequence ang production. For instance, in making a large machines, assembly is done step by step para siyang building blocks. Second, work centers. Work center is also called department. It is focused on the particular operation. Work centers are arranged to minimize the material movement, and those for the frequent interaction usually placed near to each other. Example, drilling, grinding, heat, heating, sewing, painting, shaping, and receiving. In that case, in a toy factory, different workers centers handle plastic molding, metal forming, sewing, and painting. After the parts are fabricated, they are transferred to assembly work center where the final product is put together. Ibig sabihin, ang work centers is organized the production process by function, making material flow more efficient. Third is manufacturing cell. A manufacturing cell combines of different machines into one group designed to produce products with similar shapes or processing needs. Instead of arranging by type of machine, the layout is based on the product families. The process of creating manufacturing cells has a three-step. First step, group parts into families. Group parts into families classify parts according to their processing requirements using a coding system. Second step is identify flow patterns. Determine the dominant production route for each family. Third step is the rearrange machine into cells. Physical regroup machines to form cells. If there are special machines or parts that don't belong to the family, they are placed in the remainder cell. So, ginagamit ito sa industries like metal fabrication, computer chip manufacturing, and assembly work.
Good day everyone, my topic for today is assembly line design. An assembly line uses a moving conveyor that passes through workstation. Each stations work within a fixed time, called the cycle time. At every station, tasks are done like adding parts and completing assembly steps. The problem in assembly line is how to assign these tasks. This is called assembly line balancing problem. The goal is to make sure no station goes beyond the cycle time and reduce ideal time across all stations. We also need to follow the precedence relationship, which means some tasks must be done before others. In short, assembly line design is balancing about dividing work fairly, saving time, and keeping the process in order. The steps in balancing an assembly line are straightforward. The first step, we need to specify the order of tasks using a precedent diagram. In this diagram, circles represent the tasks and arrows show the order in which they must be done. The second step, we need to determine the workstation cycle time using by this formula. Makikita nyo yan sa aking PowerPoint. C equals production time per day divided by required output per day in units. This tells us how much time each station has to complete its work. The step 3, we need to compute the theoretical minimum number of workstations using the given formula. N equals sum of the task time divided by cycle time. We always rounded this number up to the next whole number. Step 4. We select a primary rule for assigning tasks to workstations and a secondary rule in case of ties. Step 5. Now, starting assigning tasks for workstation 1, we add tasks one by one until the cycle time is reached or no more tasks can fit because of time or order restrictions. We repeat this for workstation 2 and 3 and so on until all tasks are assigned. Step 6. We evaluate the efficiency of the balance using the formula provided. The formula is efficiency equals sum of task time divided by equal number of workstations times workstations cycle time. This shows how well the tasks were distributed. The last step is step 7. If the efficiency is not good enough, we need to rebalance the line by using a different rule for assigning tasks. Example 4.2. Assemble line balancing. The model J-Wagon is to be assembled on a conveyor belt. 500 wagons are required per day. Production time per day is 420 minutes, and the assembly steps and times for the wagon are given in the exhibit 4.4. Assignment: find the balance that minimizes the number of workstations subject to the cycle time and precedence constraints. The solutions is, the first step is a draw a precedence diagram, exhibit 4.5. Illustrate the sequence relationship identified in exhibit 4.4. The length of the arrows has no meaning. The assembly step and time for Model J Wagon. In the table, you can see in my PowerPoint is have task and time, description, task that must present. In task, we have A, B, C, D, E, F, G, H, I, J. In time seconds, A have 45 seconds, B have 11 seconds, C have 9 seconds, D have 50 seconds, F have 15 seconds, and F, G, H, I have 12 seconds. J have 8 seconds, K have 9 seconds, total of 195 seconds. In descriptions, A have position rear axle support and hand fasten for screw to nuts. B have insert rear axles. C have tighten rear axle support screw to nuts. And D position front axle assemble and hand fasten for screw to nuts. E have tighten front axle assembly screws. F have position rear wheel 1 and fasten hand cap. G have position rear wheel 2 and fasten hub cap. And H have position front wheel 1, fasten hub cap. And I have position front wheel 2 and fasten hub cap. And J have position wagon handle shaft and front axle assembly and hand fasten bolt and nuts. And K tighten bolt and nuts. And task that must present or kailangan gawin bago magawa. Sa A, wala tayo kasi yun yung starting point. And next natin is B. Bago tayo mag-proceed sa B, kailangan natin matapos yung A. And yung C is same lang. Kailangan matapos yung B para matuloy tayo sa C. Ang D is wala kasi yun din yung starting point natin. Yung E is kailangan ng D. Kailangan makastart sa D bago makaproceed sa E. And yung F natin is needed C. F and G needed C to continue. And H and I needed E to continue. And J needed F, G, H, and I to continue to J. And K needed J to continue. And the ending point is K. Ang next natin is 4.5 is, nakikita nyo sa aking PowerPoint, yung starting point natin is A and D. And our ending point is K. So, sa A tayo. Sa A, ang next niya na step is B. And the next step ng B is C. And the next step ng C is F and G. And the next step is J. And the last step is K. Para matapos natin yung task sa taas. Sa task naman sa baba, which is start sa D. D, ang next sa D is E. And E, ang next is H and I. And H and I to J and J to K. Para matapos naman yung task sa baba. That's all. Thank you.
Cycle time calculation. Convert the daily production time 2 seconds for 20 minutes times 60 seconds equal 25,200. And divide it by daily output 500 wagons. The formula is C equal frac 25,200 and 500 equal 50.4 seconds. This C represents the maximum time each workstation can take to complete its task. Number 2. Theoretical minimum workstation. To find the minimum number of workstation needed divide to the total task time. T equal 195 seconds by the cycle time. C equal 50.4 seconds. The calculation is N. T equal frac 195 50.4 approx 3.87 and we round it up to 4. And number 4, task assignment rules. Primary rule: first assign tasks that have the most subsequent tasks. Secondary rule: if two tasks have the same number of subsequent tasks, assign the one with the longer task time first. Task assignments and workstation. Tasks are assigned to workstation, making sure that precedence the order in which tasks must be done, and cycle time limits are respected. In this example, 5 workstations were used. Efficiency calculation. Efficiency is calculated using the formula text efficiency frac T N A times C, where NA is the actual number of workstations substituting the values. We get frac 195 5 times 50.4 approx 77. Efficiency calculation. Efficiency is calculated using the formula text efficiency frac T N A times C, where NA is the actual number of workstations substituting the values. We get frac 195 5 times 50.4 approx 77.
Good day everyone. Today we discuss about splitting tasks. Splitting tasks happen when the longest task time in a production line is greater than the workstation cycle time. Because of this, the task limits the speed of the production line. So para iwasan ito, we need to divide into 2 or more workstations. Consider the following illustration. Suppose that an assembly line contains the following task time is 40, 30, 15, 25, 20, 18, and 15 seconds. The run is 7.5 hours per day, and the demand of output is 750 per day. The workstation cycle time required to 750 per day is 36 seconds. 7.5 hours times 60 minutes times 60 seconds is 27,000. 27,000 divided 750 is 36 seconds. Our problem is that we have one task that takes 40 seconds. How do we deal about this? There are several ways that we may be able to accommodate the 40 seconds task in 36 second cycle. We have 6 possibilities. First, the split the task. The task can be split so the complete units are processed in 2 workstations. This helps the work stay within the required cycle of time. Second, share the task. The task can be shared so that an adjustment workstation does part of the work. This is different from splitting because the other station only helps, not process whole units. Third, use parallel workstation. Sometimes it is necessary to assign the task to two workstations that work at the same time. Use a more skilled worker because these tasks exceed the cycle time by just 11%. A faster worker may be able to complete it within the 36 seconds target. Work overtime. Producing 1 unit every 40 seconds gives 675 units per day, which is 75 units short of the needed 750. To make the extra 75 units, 15 minutes of overtime are required. How we compute our overtime? So, 75 times 40 divided by 60 is equal 50 minutes of overtime. 6. Redesign. It may be possible to redesign the product to reduce the task time slightly.
Manufacturing processes are the backbone of industrial production, enabling the transformation of raw materials into usable products. These processes are chosen based on factors such as material properties, design requirements, production volume, and cost efficiency. Understanding the different types of manufacturing processes is essential in industries ranging from automotive and aerospace to electronics and consumer goods. Manufacturing processes their selection for industries to optimize production, improve product quality, and remain competitive.